So I wanted to talk a little bit about complex numbers and about this extra idea that's called the complex conjugate and why you might care about that. So when I was growing up, this was always the symbol I used for the complex number conjugate. Is you just put a little hat over the top of it. I've also seen in the textbook them using a little asterisk right there. And that just means the complex conjugate. And so there's a few things about the conjugate that are nice. So one thing is, okay, well, first off, like, what is this, a complex conjugate? So basically the idea is if you have a complex number, then here's the definition of what the conjugate is. Now, that's just a definition. So if you see a question that just asks you to calculate the conjugate, or there's a conjugate at some point in the question, what I want you to notice is that the real part is the same. So the a value is exactly the same, and the imaginary part is the opposite. Now, don't be fooled. It's not necessarily true that the conjugate has a negative imaginary part. It's just that the conjugate has the opposite imaginary part. So just as a couple quick examples, if z is equal to 2 plus 3i, then a conjugate is 2 minus 3i. If z is equal to negative 3 plus 5i, then the conjugate is negative 3 minus 5i. If the conjugate is equal to 1 minus 4i, sorry, if the original is 1 minus 4i, then the conjugate is 1 plus 4i. If the original number is 5, then the conjugate is 5. If the original number is 2i or negative 2i, then the conjugate is positive 2i. The real part's the same, the imaginary part is the opposite. So, a couple things that you might find interesting about this. If we think about a complex number being right up here, we can break that down into the real part, and the imaginary part. Well, the complex conjugate is going to have the same real part, but opposite imaginary part. And this makes some beautiful symmetry here. If we use theta to represent the angle on one side, then negative theta is the angle for the conjugate. And so what we have talked about is that every complex number can be written as r cosine theta plus I sine theta. So now we know that the conjugate is r cosine negative theta plus I sine of negative theta. But if you look over at your picture, we can do even better than that. We notice that the real part was the same as before. And this helps you remember that the cosine of theta is the same as the cosine of negative theta. It has to be to match up with the picture. So when you start doing more stuff with complex numbers, it actually leads you to some nice results about trig because they're connected to each other. And similarly, one other way to say what I just said is that cosine is an even function. The negative angle of cosine is the same as the positive angle of cosine. It's symmetrical around the x-axis. Now, if you look at sine, you'll notice that I have the opposite part of the imaginary. So I can go minus I sine of theta, like that. Okay, so that's just a nice thing about complex conjugates. Another nice thing about complex conjugates is what you get if you multiply z times z bar. You can do it using either your polar form with the cosine and sine, or with your rectangular form. I'll do it with my rectangular form for this example. A plus bi times a minus bi. So a times a times bi, bi times a, bi times bi gives me a squared plus abi minus abi minus b squared I squared. That ends up giving me, because these cancel out, a squared plus b squared. Now how did that happen? Well, negative b squared I squared, remember our whole definition of complex numbers is that I squared is negative 1. So we take that, put that right there. Double negative makes a positive. Now a squared plus b squared is actually the same as c squared. And remember, we're talking about right triangle. A squared, b squared. So what is c squared? It's the right radius. It's your distance from the origin. So you might see this formula written down somewhere, that a complex number times its conjugate is equal to the absolute value of that complex number, because that's how far it is from 0. But it's not just equal to the absolute value. It's the absolute value squared. Okay? So that's another nice thing. One last thing about complex conjugates that's really nice comes from the quadratic formula. So if you got a quadratic formula, you're saying all this fun stuff. And remember, we get imaginary numbers from taking the square root of negatives. So the square root of a negative number means we're going to have I times the square root of that number. Okay? I want you to notice that there's a plus and a minus, meaning the quadratic formula will always give you a complex number and its conjugate. So what I should say is, if the quadratic formula gives you one complex number, you're guaranteed that it will also give you its conjugate. And so I want to prove that to you. If we look at a quadratic equation in terms of complex numbers, and we're going to assume that let's not use a plus bi, because I already got a and b in this problem. Let's assume x plus iy is a root. That means that if I plug it in, that's going to equal 0. Now there's so many letters going on here. I'm not going to get like a satisfying number answer. I'm going to get a result. If I square this out, I get x times x times iy, another x times iy, and I squared y squared. If I distribute this out, I get bx plus biy, like this. And what I'm going to do is I'm going to gather all the real parts and all the imaginary parts together. So remember, our I squared, I'm going to replace it with negative 1. So my real parts are ax squared minus ay squared plus bx plus c. My imaginary parts are 2a xiy plus biy, and that's equal to 0. So this chunk right here is the real part, and then this chunk right here is the imaginary part. What I want you to watch now is I'm going to go back through and replace what I plugged in with the conjugate. So I'm just going to write on top of it. So instead of plus iy, I have minus iy. So what does that do? Here, it makes this into a negative 2. This part, the I squared y squared, remains positive because I had a negative iy times another negative iy. And this part over here becomes a negative biy. What I want you to notice is the real part is the same, but the imaginary part is the opposite of what it used to be. So for our original number, when we plugged in z, what we had is that whole thing needed to equal 0. In other words, the real part equaled 0 and the imaginary part equaled 0. When we plugged in our conjugate, we got the same darn real part and we got the opposite of the imaginary part. Well, if the original real part equals 0, if this, then that must also be true. Thus, z star is also a root. So I just wanted to show you what the conjugate was, what it means visually, how it relates a positive angle to a negative angle, how if you multiply a number times its conjugate, you get its magnitude squared. So it's kind of like doing the dot product. If you remember doing the dot product from before, if we have two vectors and we dot it with ourselves, we get a squared plus b squared. It turns out to be the exact same thing you get when you do z multiplied by z conjugate. And this last one, that if you solve a quadratic and a complex number is one of your solutions, the conjugate has to be the other solution. So thanks for watching. Let me know what was confusing, and I'll help out.